Hello, IB. We're looking at 16b, which is how do we decide whether a function is increasing or decreasing, or possibly doing a combination of both if it increases and decreases along the entire domain. So what we describe as increasing is as x increases, does y also increase? Or decreasing, as x increases, so as you're looking from left to right, does the y value decrease? So does it go down? So in terms of what your book tells you, and just looking at this first example, if S is an interval in the domain, so for example, if my S is maybe from this origin here to this point here, let's call that our interval S. So that f of x is defined for all x in S. So in other words, we have a y value for every single x value that's in this interval, which we do. So this entire interval is full of points and all of them are defined and they match up. F of x is increasing on this interval S if and only if. So this double arrow means if and only if, or IFF sometimes is shortened as, the function at the first x value A is less than or equal to the function at the next value B. So for example, if this is my A value, this is my B value, the function at A is smaller than or equal to the function at B. So yes, it is, because as I move to the right, it increases. And then vice versa for decreasing. So if we look at this function x squared, it would be decreasing when x is less than or equal to 0. So right here, everything to the left is decreasing, because as I look from left to right, so I'll get rid of that arrow in case that's going to be confusing. But as I move from left to right, I always read, just like you read a book, you read graphs from left to right. So if I follow from left to right, I am going to be decreasing as I approach 0. And then afterwards will be increasing when you move from 0 toward infinity. So then the question is, what's happening at 0? All right, technically at 0, nothing's happening. We come to a complete standstill because we were decreasing and we stop, we change direction, and we begin to increase. So there's a lot of dispute out in the math world whether we say an interval is less than or equal to or greater than or equal to, because technically equal to 0, nothing's actually happening and no motion is actually occurring. So when we have that split second in time that x is equal to 0, our object, or whatever we're mapping, actually has a speed of 0, which means we stop, we change direction, possibly, and then it begins to move again. There are some functions that are monotonic functions. So monotonicity just means that for the entire domain that we talk about, it is only increasing or only decreasing. So if you're looking at a specific function, think about a few now that would only be increasing or decreasing along the entire domain. So for example, an exponential function, it continues to decrease throughout the entire domain of the graph. So therefore, this is a monotonic function. It is only decreasing, or a logarithmic function that is only increasing. So it doesn't have a change in direction from increasing to decreasing. We call those functions monotonic, and we describe it as monotonicity. So now we're wondering, how do we decide whether a function is increasing or decreasing using calculus to support our conclusion? So even though you guys are given x cubed minus 6x squared plus 3x minus 1 as this purple function here, so we'll call this function y. So it increases, we can see that, and then it changes direction, it begins to decrease, changes direction again, and then it begins to increase. What we're looking at is if we took the derivative, which is this y equals 3x squared minus 12x plus 3. So we'll call this y prime for the moment, because if you take a look at what's happening with y prime, which we've already talked a little bit about in the last chapter, but as this purple function is increasing, you'll notice that your first derivative is above the x-axis. So it has a positive y value. As the purple function begins to decrease until about here, your red graph is below the x-axis, which means it has a negative y value. And then right about here, when it changes direction and your purple graph begins to increase, your red graph, or the derivative, is going to have a positive y value again. So now you guys have basically the red graph mapping the increasing, decreasing, increasing of the purple graph. So your red graph is basically telling you what direction we're moving in. Are we increasing, decreasing, increasing? What's happening? So the red graph is going to be telling us information about the original function y. So for us to prove that, what we're interested mostly in is these change in direction positions, because we know that we're either going to be increasing or decreasing, and then something happens when we change direction. So whenever we change direction, we're talking about the motion being 0. So our first derivative is going to equal 0. So our first step is we're going to we will set the derivative equal to 0 to find when the rate of change is 0. So for us, that means we'll set 0 equal to this 3x squared minus 12x. We'll wind up factoring out the 3. We're dividing 3 by 3, so really we're looking at x squared minus 4x plus 1. This is not going to factorize, so then we need to consider how do we wind up solving for x. And I think it'll be pretty quick here if we go ahead and take x equals negative b, use the quadratic formula, plus or minus the square root of b squared minus 4ac, and then all over 2a. So remember, you guys have options here. You can also graph this function. You can graph x squared minus 4x plus 1 and look for the x-intercepts. Either way, you're going to wind up with 2 plus or minus the square root of 3. And that means that x is going to approximately be 0.268 and 3.73. So if you guys can double check that, make sure you guys are getting the same thing. And if we look at our graph, notice at 0.268, right where we wind up crossing the x-axis, and 3.73 again is when we have a change in direction, or it's when our derivative crosses the x-axis. So we're starting to pick up on patterns here. Our derivative hits the x-axis every time that our original function changes direction. So remember, we're using our derivative to tell us information about our original function. So our original function is what we really want to make sure we are describing when we write any kind of conclusions. So first of all, we found our x-intercepts, which means we have found 2 changes in direction. So if we have 2 changes in direction, what we're interested in is what happens before that change, what happens between the 2 changes, and what happens after the second change. Because we're not sure yet. If we didn't have this graph in front of us, we wouldn't really know if the original graph was increasing, decreasing, increasing, or maybe increasing, or decreasing, increasing, decreasing, whatever the case is, we need to check that. So we have 2 changes in direction, and now we're going to use a sign diagram to prove what happens between those 2 changes. So with a sign diagram, we wind up thinking about what happens along that x-axis, or as you look from left to right. So I know that I have something happening at 0.268. I've got another change happening at 3.73. I'm using my derivative to tell me something about my original function. So I'm going to have a conclusion where I talk about my original function f, but I'm going to use my derivative to help me describe it, which means I want to use my derivative with a couple test points to see what's going to happen to my original graph. So I'm going to choose any value from negative infinity all the way up to 0.26, something easy, so maybe -1, an easy number to substitute in. I'll pick a number between these two, so let's pick a +1, something after 3.73, maybe 4, and then that'll tell me what's happening all the way up to infinity. So if I choose a test value of -1, I'm going to sub it into my derivative. So let's go back up to where my derivative is. So if I substitute in -1 into my derivative, I'm looking at 3 times -1 squared minus 12 times -1 plus 3. So I won't show my work for this test value every time, but I do want to make sure you guys know what you're doing. You're taking this test value and substituting it into your first derivative, and we're really looking to see, is my first derivative going to come out as a positive or a negative value? If it's positive, that means it would be here above the x-axis, which represents my original function increasing. If it's negative, it would be below the x-axis, as the red graph is, and it shows that my purple graph, the original, is decreasing. And again, same thing. If it's positive at the end, then I want my purple graph to be increasing, which means my red graph will be above the x-axis. So it'll have a positive or negative y value. So for this one, I already know what it should be. It should come out to be positive, negative, positive. And by substituting in a value, I'm algebraically supporting the fact that the graph shows me that. So I do wind up with a positive value, a negative value, and a positive value. So if I did not have that graph, I would know that this cubic is going to increase and then decrease, and then it's going to wind up increasing again. So I would have a very general sketch of what's happening with my function. Once I finish my sign diagram, we always want to make sure we write a conclusion. So we can say that f of x is increasing when x is smaller than 0.268 and greater than 3.73 and decreasing between the two. Now, you'll notice that your textbook winds up using the equal to for all of these. And there's a huge debate. Different textbooks have different things, and different mathematicians think different things. Technically, there's nothing actually happening at 0.268. However, just know that your textbook will always have an equal to, because that's how the IB textbook is written. However, nothing is actually happening at 0.268 or 3.73 because that's where the change in direction occurs, all right? And we'll talk a little bit more about that in class. So let's just go back through our steps. In order to describe whether a function is increasing or decreasing, we use calculus to support this process. We take the derivative and set it equal to 0 to figure out where the changes in direction occur, where the rate of change is 0. We find those x values, and then we're going to set up a sign diagram so we can test values. You can choose any value you want that's below the first x-intercept or change in direction, between, and after. So any number you want, just pick easy ones that you can substitute into your derivative, and then you can make a conclusion about your original. Let's do one more together, and then we'll leave you guys with the third one. So this next example asks you guys to consider a rational function, which already we know we're going to have vertical asymptotes that will affect our our changes in direction when we look from left to right. So we want to make sure we also include vertical asymptotes, and we're going to make a sign diagram to support whether the graph is actually increasing or decreasing. So step one again, we're going to find, because it does say to show, so we're going to find our first derivative by using the quotient rule. So the derivative of the numerator is 2 multiplied by the denominator minus the derivative of the denominator multiplied by the numerator all over the denominator squared. Go ahead and pause here, guys, and try to clean that up a little bit. And then when you push play, you can see if you match what I've cleaned it up as. Please double check that you guys have matched that. When we set our first derivative equals to 0 to find the changes in direction, we can automatically notice that with a fraction, the only way a fraction will equal 0 is if the numerator is equal to 0. So what we want to really focus on here is the numerator equaling 0. And this is one that factors nicely. So I can take out the common factors. So the negative 2x, I'll be left with an x and a minus 3. So therefore, x is going to equal 0 or positive 3. So I do have two changes in direction at 0 and positive 3. What I need to include, the big star on this one, is that I also have vertical asymptotes. And when I read a graph from left to right, if I notice that my original function is a fraction, it's a rational function, I need to check for the vertical asymptotes. And remember from our functions unit and throughout the year, that vertical asymptotes occur when your denominator is equal to 0. So I'm going to set my denominator of x squared plus 2x minus 3 squared equal to 0. The square, again, square root of 0 is 0. So I'm really just looking at x squared plus 2x minus 3. This factors nicely. So we'll go ahead and factorize, and we have x, we've got 3 times 1 minus 1 plus 3, that'll make the 2. So therefore, when x is equal to -3 and +1, we have vertical asymptotes. With rational functions, I need to include both of these, when the derivative equals 0 and the vertical asymptotes. Any values that I find, I need to include in my sign diagram. So again, I set up my sign diagram. I'm going to be using my derivative to now tell me something about my original function. And I do want to use a different way of noting what I'm looking at here, because at -3 and at +1, I have a vertical asymptote. So I'm actually, those aren't changes in direction, but I do want to include them so I know that we're approaching an asymptote. So I'm going to make those blue and dotted for vertical asymptote. And then at 0, so right here is 0, I actually have a change in direction. And at +3, I actually have a change in direction. So now I need to choose test values to figure out what is happening before 0. So is my function increasing or decreasing before 0? Because here's my change in direction. And then at 3, so between 0 and 3, what's it doing? And then after 3, what's it doing? So I only change directions twice. But remember, if I'm decreasing here and I approach an asymptote, that means I'm going to have to be getting closer and closer and closer to that asymptote. So they still are very important to include so I know what the picture looks like. So let's choose a few test values. You can choose a test value for all the intervals or just below 0 and above 0 between 3 and then above 3. So let's choose something like, let's say -1. And let's say maybe a +2. Go ahead and substitute those into your derivative, and let's see what signs you get. So before 0, the derivative winds up having a negative value, which means everything before 0 is negative. And after 0, we wind up having a positive value, positive derivative value. So that means our positive after 0 here and here. And then, oops, we didn't test after 3. So we need to put one more test value in, maybe choose 4. If you substitute 4 into your derivative, you actually wind up getting a negative value. So just to see what this graph is actually doing, let's just draw a little sketch. We decrease as we approach this asymptote. So we're going to go along the asymptote. Then we continue to decrease, but remember, we're approaching the asymptote, so that means now we need to approach the asymptote and decrease on this side. And then we hit 0, and we begin to increase. So it looks like we have a little bit of a parabola there in between the two asymptotes. And then I increase again until 3, and then you wind up decreasing again after 3. All right, guys, so when we're writing our conclusion, I'm just going to show you one other way that you can write this. F of x is increasing between 0 and the asymptote at 1, and then from 1 until the change in direction at 3. So nothing's happening at 1, and nothing is technically happening at 0 or 3. Another way that IB allows you guys to write your notation is using brackets. So you could even use interval notation saying from 0 to 1, but not including 1. And then that happens again, increases again from 1 until 3. And we use this union to say that both of these sets, these intervals, are actually showing increasing values for our function. If I'm decreasing, I decrease from -infinity until -3. And then again from -3 until 0. And then again from 3 to infinity. And again, all of these are going to be connected with the U, just saying that I have 3 different sets. So you can either use the interval notation we used on the last question or the brackets, and they are both acceptable. All right, guys, we're going to put up this last question for you. You try this one on your own. All right, and oops, take that away. You try this one on your own, and we'll see you guys in class. Have a great night.